Hey there, and welcome back to Astronautical. The rocket equation. Sounds like a really complex mathematical equation that requires heavy calculations. Yes, you're right. After all, it is rocket science, but after this video, you should have a fair understanding of what the rocket equation is and what it means for rocketry. Let's get spacey. Okay, let's start off with a question. Why is it so hard to get into space? Why do we use these gigantic rockets with thousands of man-hours put into building them? The answer is, it takes a lot of energy to put something into space. Let's take a situation of putting a tiny satellite, or a CubeSat, weighing 1 kilogram around Earth in an orbit. From high school physics, we can find the potential and kinetic energy required. Using the respective equations and assuming that we take it up to about 400 kilometers, neglecting that Earth's gravity is an inverse square law, and taking a value of 8 kilometers per second for our final velocity in orbit, we get a total required energy of 36 megajoules. Okay, now that sounds like a lot of energy, but let's try and see how much it costs. Converting this value into kilowatts, we find that it is equal to 10 kilowatts. A typical kilowatt of energy costs about 10 cents, so 10 kilowatts would be $1. Now, this doesn't really seem expensive, yet we hear about each rocket launch costing millions of dollars. That's because there's one major thing that we're forgetting about, which is that creating all this energy requires propellant, which has mass. So, we need propellant to carry our satellite, and more propellant to carry this propellant, and even more to carry this one, and it goes on to a seemingly exponential runaway. This is where the ideal rocket equation comes in, and determines how much of a rocket needs to be filled with propellant, and how much of it can be useful stuff, also known as payload. So, we're not going to dive into the derivation of the rocket equation, but we are going to look at what the final equation actually is and what it means. This equation here is called the ideal rocket equation for free space. What this means is that the equation deals with rockets in a vacuum and neglects the effects of air resistance. So the equation here relates the maximum change in velocity, or delta V, of the rocket to the exhaust velocity of the propellant on board and the initial and final mass of the rocket. So let's break it down and look at what the different symbols represent. Starting with the delta V here, it indicates the change in the velocity of the rocket. Let's take, for example, a simple rocket with no stages that goes into Earth orbit. The rocket goes from being stationary with zero velocity to about 8 kilometers per second. So the delta V, or change in velocity, would be in this case 8 kilometers per second. Now, moving on to the right hand side of the equation, this symbol represents the exhaust velocity of the propellant that is shot out of the rocket. Let's go back to the example of our rocket here, and now the exhaust velocity is the speed at which the propellant is burnt and shot out of the engine nozzle. The next term in this equation involves a mathematical function known as the natural log, and these two terms here are the initial mass and the final mass. Let's look at what these two are on our example rocket. So, a typical rocket will have a payload with some mass, some propellant to burn, and a structure to hold everything. The initial mass is the sum of all of these, or simply the mass of the rocket before it starts moving. Now the final mass after reaching Earth orbit is going to be everything you had at first, minus the propellant, because it was used up in getting up there. Okay, so now that we have an idea of what the different components of the rocket equation mean, let's look at what it implies for a rocket and its payload. Using the rocket equation and manipulating the masses and other terms, we can end up with this equation, which can give us what is known as the propellant fraction of a rocket. That is, when you start with a rocket on the launch pad, what fraction of its total mass has to be propellant in order to get to the velocity you need. Now let's plug in some numbers and observe what happens. So for a rocket to get into orbit, it needs to go from 0 to 8 kilometers per second. That's your delta V. Suppose we use a solid rocket with a typical exhaust velocity of 2 kilometers per second. Solve the equation and we find that 98% of our rocket will have to just be propellant, while only 2% of the mass can be used for the payload and structure. Now let's double the exhaust velocity from 2 to 4 kilometers per second. Solving the equation, we find that now 86% of the rocket will have to be devoted to the propellant, and 14% can be used for the structure and payload. This is the critical thing about the rocket equation, because changing the exhaust velocity by just a factor of 2 has led to a 7-fold increase in the mass of our rocket, which can be devoted to the structure and payload. And that's the ideal rocket equation and its implications. This video was a relatively complex one, with slightly more mathematics, so feel free to go and rewatch any parts of the video. Be sure to like and subscribe and check out other content on the channel. Well, that's all. Stay spacey.